safe technique when you come to larger problems. Larger problems tend to have small bits in them. And if the small bits go wrong, then you're wrong. That's all there is to it. So this example is a very simple one. There's Bayesian analysis on the left over here and frequentist analysis over here. But all it is a uniform probability across a disk. Simple. I think everyone's still looking at the screen and doesn't look particularly puzzled by that. If I knew y, the 50% range for x is one of these arrows, and those intervals span out an ellipse, taking half the area of the sphere. Similarly for y. Okay, what happens? Yeah, arrows are working this time. What happens when you observe y? Y is some data value d. What do? Well, d is there. Well, it should be rather obvious what you're supposed to do. And this is the Bayesian analysis on the left. Y, this number is d. It has no choice because it has been measured, observed, fixed, known, assigned, whatever you want. And the other bits of y, what it might have been but wasn't, aren't there anymore. They're shaded out, they're crossed out. So the implication for what x is that it's somewhere between the left and right of this sphere, with the middle 50% being the interquartile range. And that's right. You don't need fancy mathematics or formula or anything to show that that's right. It's just basic elementary logic. It really is just basic elementary logic. Frequentists look at it the other way around. They think, well, what could x have been? It could have been anywhere here. If x was here, along that arrow, that would be the 50% interval of what the data might have been if x was this value. And if x was this value, it would be somewhere up and down that arrow as the central interval of where the data might have been. Okay, these are various hypotheses. Which arrows work? Well, whenever that data horizontal line goes through one of these arrows, that is a plausible hypothesis because the data could have been d. And so the frequentist interval, confidence interval, which is an annoying word because it gives the idea to the uninitiated that one ought to have confidence in it, which you shouldn't. The confidence interval is this red arrow here. And you may notice that it's rather different from the Bayesian arrow. And it's simply wrong. In order to generate the frequentist interval, you need to think about what the data might have been but were not. So you're using all this area here that should logically be crossed out and which has zero probability after you know y equals d, because you know definitely that y is not d. And that means that this analysis is conditioned on falsity. Now, if you know any logic at all, you'll know that if you introduce falsity into your analysis, you can prove anything at all. And that's not good. That's not rational. You can move this red arrow, this frequentist interval, anywhere you like. It's an interesting parlor game to play around with what the shapes here are for y not equal to d, because you can do anything you like. in the region that's impossible, and it shouldn't make any difference. Now, I do not know why people still give frequentism house room. I just don't know. Zubin was soft on that last night, and I wish he hadn't been. I'm not. This doesn't mean I'm a fanatic. You know, people say, you know, well, perhaps it does, but if so, I'm fanatically in defense of what is right as opposed to what is wrong. And I'm not going to apologize for that. Right, talk proper. I have hobby horses, you see, that's one of them. I'm talking about big spaces. And last time I introduced the idea of nested contours, nested sampling as I call it, where you start with a prior region, take a random point, throw away everything outside it, take another random point, throw away everything outside it, and keep going, and in this way compress, shrink towards the answers you want, the optimum or the posterior or whatever it is, but increasing the quality of your samples. And in one dimension, we're just slicing into the unit line, the unit mass that was in that original domain, coming in by a random factor each time. And I just flashed up the idea that simply by doing this in sequential compression, we can map out the quality as a function of volume, technically prior mass, but think of it as volume, and get the area under this curve. So you get an estimate of the area simply by adding up the rectangles. Okay, it's statistical, because these numbers, that's actually a random number between 0 and 1, and that's the product of that and another random number between 0 and 1, and so on. So this is statistical. We don't get absolute answers, definitive answers, but we do know what the errors are, because we know what a uniform distribution is. So we do get a statistical measure of this area. If Q doesn't mean anything, of course, then the area doesn't mean anything either. So you're just playing mathematics symbols. But hopefully, your Q does actually mean something. And I'm going to take the application where Q is likelihood, a probability of getting data given your prior model. This is rational inference. This is not frequentism. It's Bayesian analysis. And I should say right at the beginning that the sum and product rules of probability aren't arbitrary. I've been around in this game long enough to remember arguments about this where alternatives were seriously proposed and volumes written on this. It all faded out in the end, but it was a confounded nuisance when it was in play. Fuzzy sets and stuff, fuzzy logic. The ordinary rules of probability, which are just the ordinary rules of proportion. There's nothing magical or difficult about this. This is simple, okay? Simple. Are forced on you by symmetries of what you're looking at. If I'm thinking of stuff, ideas, hypotheses, propositions, marbles, planets, whatever, that I can shuffle around without changing the overall amount of stuff I'm interested in, then I'm forced to use addition. Try any operation other than plus, and shuffling around gives you some different answer. If I tried putting a hypergeometric combination in there, it would all go wrong. The symmetry, the fact that I want shuffling and variance, forces the sum rule or something isomorphic to it, like multiplication if you take exponentials. And similarly, if you want your analysis to work independently for different problems, so if I have two different problems and decide to analyze them in the same framework, just put them into the computer together, I would like the results to be factorized. And that forces multiplication on top of this. And this is the multiplication rule, written down with the data instead of y explicitly as Bayes' theorem. I've gone a bit slowly over there because I do want to stress the point that there is no alternative. And the justification of that in the math detail, that's another lecture in its own right. But since the result is obvious, I don't want to waste your time by going through that. It really is logically required. There are two inputs here, and there are two outputs. Input of likelihood is obvious. That's how likely the data were given the hypothesis that went in. Historically, a lot of people try to get away without having to assign the prior. Let the data speak for themselves, all that. Well, if you have tons and tons and tons and tons of data, you know, your billions of images training set, maybe you can do this, but you certainly can't in principle, and you can't in small toy problems, and so the calculus should require you to put this in, because until you have some idea of what you're looking at, you've really got no idea how important the modulation is. So prior times likelihood is joint, and that's got a normalization number called the evidence, or prior predictive, or marginal likelihood. Loads of names for this, which reflect the confusion that there's been in the subject for the past century, times the posterior, which is the shape of the distribution. And I've written the prior and the posterior, which are shapes. I've written them as measures, just to stress them, with D's in, just to stress that. These are inputs. Assign what you think might be reasonable. This is the likelihood which modulates what you thought might be reasonable, and you end up with the evidence and the posterior. That's the fundamental structure of probability theory, however you want to apply it. I haven't defined for you what X is, what you're looking at. They could be weights in your neural nets. I don't care. It could be the temperature of Saturn. I don't care. This is general stuff. And what I'm actually wanting to do today is get across ideas, a mode of thinking, which you never need to think about again once it's in your DNA, once it's in your head. And the techniques, you just do them, hidden away. The substructure of the real problems that you people actually want to be dealing with. So this ought to be unimportant. Anyway, the integral is equation 1, because you can't really get a shape from a joint distribution until you've divided out the normalization. So logically, the evidence is actually important. It's fundamental and essential, and it's how you compare different models, different priors, so that you can compare objectively. You've got an objective measure for deciding between your different models. And if you think you're better than your professor, you'll be able to prove it. So this is what we need to do in probability theory, is work out the evidence and posterior. And that's easy. We've already got the technology. Because the nested idea of compression just brings you in abstractly. You don't have to have a meaning on that. But it's nice if you do. In probability theory and inference, quality is just the likelihood function. And here we have that set of rectangles, and Z is the area. I've mentioned that you don't get it to full accuracy because the abscissas along here are statistical, and incidentally that variability overrides your choice of which way around to draw the rectangles. I've drawn them outwards, I could have drawn them inwards. It doesn't matter. Okay, so what's going on here? That's an alternative view. Here's the quality, now called likelihood, and given the symbol L up the vertical axis. And here's X, the amount of X space that's enclosed by these shrinking contours. And at some point, I've got to some amount of shrinkage. I'm throwing away everything on the outside, only considering what's inside. And when I take a new random point inside, X shrinks by a uniform random number, and L will then increase because I will have come in. So this is the compression loop. Start here, start an iterate here at X with its likelihood L. Set a limit L star, the top, which is just L of X, and then shrink down by a uniform random number. And I mentioned last time that the log of the volume, the logarithm of the volume, decreases by about 1 power of e on average per step. So it's very simple and straightforward. And that's compression. Now, what I only realized recently was that exactly that same simple philosophy of sampling inside a hard-edged box actually lets me sample a likelihood function as well as compressing it. And indeed, when I talked about this on Monday, introduced the compression idea, a couple of people did ask me, can I go out again? Because the metropolis exploration, the 20th century exploration algorithms do come in and out. They want to explore a probability region. You don't want to just shrink. You've got to wobble around sideways and in and out. So they need to be able to retreat. And actually, this is remarkably easy. All we do is instead of setting my upper limit on likelihood to be what the likelihood is at my current point, let me relax that a bit so I could go outwards again. And let me relax it by, guess what? A uniform random number. L star is U star L of X. So I come down here in likelihood by some random factor. And then come out again, resample within this relaxed, larger volume. So I'll get X primed is another random number times wherever I got to here. So relaxing L implicitly relaxes X, and then sample from inside the relaxed X. And keep repeating that. The loop now has one extra instruction, which is that multiplication. That's not too hard to program. So instead of just keeping L star fixed, L star is reduced. So as well as having a step where we shrink in volume by a factor of e, we've also got a step in there, in the iteration, a step in which the likelihood shrinks by a factor of e. So each step here comes one down in likelihood, one down in likelihood, and one in volume. So we are going to get an algorithm which will converge to points around the 45-degree slope. Just see it in the picture. If you're steep here, then the -1 is going to win this way, and the other way around this way. So the points will move in, but it's randomness in there, so you will settle down around here. And what this does exactly is sample the posterior proportional to the likelihood, which is exactly what you want for probabilistic exploration. This is actually no different from the metropolis technique, which you all know and love. It's no different. I'm just putting it in different words. What the metropolis and co. the 20th century said to do was take where you are, go somewhere else, and check whether you're inside, check whether you are or are not in or out of that L star, which is some random number. If you've come down more than that random number, you keep it. If you haven't, or the other way around, whichever way. Anyway, that's the way it works. This is standard metropolis, but I'm just explaining it the other way around. Now, going from nested sampling to exploration, from compression to sampling, involves multiplying by a random number, so that's quite easy. The corollary of that is that if you leave that random multiplication out of your program, leave it out of your exploration program, then you've got the compression algorithm. So the same programs that you have been using to explore and sample, if you take an instruction out of them, they will also give you the compression. So the same programs that you have been writing to get the posterior distribution will also give you the evidence value. You get two, literally for the price of one. Both halves of your Bayesian inference, evidence and posterior, come out from the same program that you already know how to do. That's neat. So, okay. Story so far, doing it for the 21st century. Compression is what we need to get to the evidence, because the evidence relates prior and posterior. And you need to do that in a controlled fashion in order to get the connection in a controlled way. Exploration within a hard-edge box, I'm suggesting Galilean Monte Carlo, so that you can get systematic motion through this volume, bouncing off the edges when you have to. And this gives us inference, gives us a paradigm, standard way of thinking about doing inference. You get evidence and posterior. Any questions on this? Any points anyone wants to raise? Yes, Nico.
So your algorithm for estimating evidence involves an optimizer. You're optimizing the likelihood.
I would prefer to say that I'm exploring the likelihood. As a side effect, I will end up optimizing the likelihood, because I'll come in by shrinking the volumes, I will send it up. And in fact, I use these programs as my favorite optimizer.
The optimization is too fast. If you're getting to the maximum likelihood in very few steps, will that mean your evidence approximation is going to be bad?
It would if that was possible. But it isn't possible. The reason is that I shrink by a factor of e each time. I don't care how fast or slow the quality changes. At the second or third step, when I've hit 2 and I want to be inside 2, I don't care how extra bright this central region will be. I'm exploring across a flat distribution. That's what the maths tells me to do. So you're in fact anticipating what I'm going to be about to say, which is always good when someone in the audience anticipates what I'm going to say because they haven't got lost. Anyone else anticipating? Never mind. Yes? Oh yes, multimodality is indeed an issue, and again, I hope to come to that. Good question. I like this. Any more questions telling me what I need to say in the rest of my talk? Oh, what about bimodality, multimodality? What happens to the exploration? Well, the exploration may get trapped. Yes, I'll come to this. Sorry, Hans, you're quite right. Anyway, what I want to do now is move on. What I want to do is move backwards to how people have been doing things and try to show you why these computations have been thought to be difficult. I think that's this perceived difficulty has been damaging to the progress of inference and learning and the whole slew of scientific progress generally. The 20th century gave us the standard metropolis algorithm, but for compression it gave us simulated annealing, and for exploration it gave us Hamiltonian or hybrid Monte Carlo as the canonical standard methods. These are not wrong. If they were wrong, that would have been seen long ago. And their authors are bright people, and it would never have happened. But I don't think they're general enough. Let me start with how the 20th century would have told, or did tell us, how to do compression. The need is to start from a prior distribution and compress it down to or through the posterior distribution. To get that connection in a controlled fashion, we know what we're doing each step. The trick is to generalize the likelihood to a fractional power. Okay, well, this is mathematics. You know how mathematicians behave. You have an aim, and you say, consider this strange expression, and somehow your answer magically drops out from this strange expression. And the author preens himself, thinks he's very clever, and the students think it's genius. And it just isn't, comes from experience. Anyway, I burble. I track beta from 0, when L to the 0 is 1, so there's no modulation at all, and that's the prior, through to beta equals 1, which is what I want, modulation by a factor L. And what that does is follow the log L log X curve. I've now put logarithms on there, and end up at the 45-degree slope that I showed you earlier. Here, the shrinkage in likelihood, if I do the sampling, wins over the shrinkage in volume, so I move upwards. If I were to get out there, I would shrink downwards. So that's all fine, and I get a stable exploration at the 45-degree line. Fine, that's what we want to do. Unit temperature. These people usually have, well, like me, have a physics background, so they think in terms of physics. And in terms of physics, you would say, oh, well, fractional powers, that reminds me of exp energy over kT, Boltzmann factors. So beta is an inverse temperature. So this is physics. L is a log n, is an exponential of entropy, and all this. That's just terminology. It doesn't affect the symbols. But the problem here, as you will have been seeing on the right-hand curve, is that if I follow the tangent here, that's fine, provided I'm on the outside of the curve. But what happens if the curvature goes the other way? Here is a stable regime, numerically. Here in blue is a stable regime, numerically. And what happens in the middle? What happens in the middle is that if you start with a prior distribution, very hot, molecules going here, there, everywhere, the prior, infinite temperature, and cool it down, and cool it down. This is all fine. And then you'll be cooling it down, and then your particles will say, woo! And they'll jump up here. My analogy here is steam and water. Actually, we've got exponential jumps in volume. Steam to water is only a couple of thousand or so, which is negligible. You could cope with that, but you can't cope with exp of 2,000. And you'd end up with supercooled water, which is just not what you want. And the whole thing would work the other way around if you tried to warm up again. So you get a hysteresis loop, and the conclusion of that is that you would lose touch with the evidence value. So you'd lose, even if you did manage to end up with there at unit temperature, which you might not because you might miss it and not realize it was there. Even if you did end up with it, you wouldn't know how important it was. So half the power, the fundamental part of the power of Bayesian techniques, would be denied you. I think this is part of the reason why big problems have been thought difficult, because all the interesting problems look like this. And so you're stuck with doing, in quotes, simple problems that are accessible to this cooling technique. Now, again, I'm talking physics language here, and I don't want to stress that, but I am talking about phase changes. And the transition from steam to water at 100 degrees centigrade is an obvious model anyway, even if you don't know physics to any great depth. And physicists do call these things a phase transition. This is a first-order phase transition. Second-order phase transitions are where this is a straight line. Things like Ising models, Potts models, some of you may have heard of these, and they have specialized algorithms for how you can cope with these things. that's difficult. The first order phase transitions have been thought are impossible. Now, look around you. Everything in this world that's interesting is in a phase, a little island which is isolated from something else it could have been. If it was not like that, if the world wasn't like that, we'd just have a planet of grey goo with no structure in it, just one big woofly domain, and we wouldn't be here to discover that it wasn't interesting. So, now, don't worry about that. But what the geometrical compression does, what I'm recommending, is that you come in by a factor of e every step, unit steps in log x, and it just doesn't matter what the likelihood does. You just come in and in and in and in and in. That's all there is to it. Does that answer your question, Nico? Good! Well, let me tell you that it does answer your question. You have to think about, the key is to think about, understand why that's unstable. If you see that, then you'll see this. Another way of saying this is that if you want to drive on temperature, which is driving on the slope of the tangent, you're in trouble when you have to go up and down and up again. Because the tangent is no longer outside, you're not separate on this point. As soon as you get inside, things bifurcate. Whereas if you just come along the axis, there's no way that can happen. It's a one-dimensional exploration. This is perhaps displaying my own origins rather than being informative for you. I don't know. Depends where you come from, and some of you will come from my place, some of you won't. But what putting L to the beta is doing is making a new function, z of beta, with z of 0 is 1, the prior, and z of 1 is the evidence we want, subtract from 0 to 1. But what you're doing in there is a Laplace transform. If L is exp energy, what you're working out there is a Laplace transform. Anyone with experience in numerical inversion will know that Laplace transforms are almost impossible to invert. If you've got a mathematical formula for it, analytic expression, you can do that sometimes, but you can't do it numerically. And the reason is this. Sorry about this. If I have some function of x and I Laplace transform it, Laplace transforms all look like that. They're decaying curves. You're doing integral f of x e to the minus sx dx, and that's the transform as a function of s. I mean, there's differences in detail, but they all look the same, and so you can't go back. It's very, very ill-posed. It's the classic ill-posed transform. So it's numerically terrible news. What have I got next? So I'm recommending you compute directly, yes. Now, I'm saying here that this is where your multi-modality question comes in. That's where I'm showing it. You can deal with phase changes, yes, and also with multimodality. Now, one can't, in any statistical exploration, cope with all multimodality. That would be impossibly ambitious. My joke about this is that no program will ever find the flagpole in the Atlantic. If I have a wide region and I'm trying to find optimum height and there's a flagpole in the middle of the Atlantic, I won't find it. You know, there's too many waves and so on everywhere else. You won't find it. So we cannot hope to do everything. But what we can aim to do is do as much as we're allowed to. And that, I claim, I believe, is assisted by being simple. Simplicity is generality. Simplicity is power. Now, what would happen in a multimodal problem? I should have got a video of this and I haven't. Apologies for that. So you'll have to use your imagination. What we do for a start is take a point anywhere in the prior region, bounce, bang, there. And then we'll throw away everything outside that and come in and in and in. And you climb up the contours in that diagram, one side or the other. Basically, your chance of getting into any of these modes will be proportional to the cross-sectional area, the basin of attraction, size of the basin or peak, whichever way you want to look at it. So you won't find the flagpole because it won't have any volume. You'll never be inside its region of attraction. And if you do this again, because this is a statistical technique, just to do it again, you may well end up with some of the points in here and some in here. Now, what you can do then is realize that each of those points has a trajectory, it has a history, it has an evidence value. So the points in here that end up on that peak will have evidence values, and so will those. But if this peak has more evidence, it's higher to compensate for its somewhat lower volume, then those points will be the better ones. So you can weight your points by evidence. And as long as points do get into the higher peak, then you'll locate it quantitatively. So this is not an absolute method for getting rid of all multimodality, but I think it's what we're allowed to do. Actually, technically, and this was actually in my 2004 paper and in the book, it's better to take multiple samples. Suppose I end up with, at some stage, within some contour, say this contour. I've got a few points in here and another few points in there. And I keep increasing the likelihood. Now what I do if I have a certain number of points, I don't have the view graph of that. I don't have the slide of that. Sorry, so I'll have to use this again. And some of you won't be able to see it properly, but most of you will, I hope. There are 6 points. The outer one is this one. I'll throw it away. Now, with only one point in the ensemble, there's nothing I can do except move it around by Markov chain to get somewhere else that'll be in here. But if I have several points going at once in parallel, so I'm now cooling not just an atom, but a whole cloud of atoms, an ensemble, then I want to duplicate anything, and I might end up duplicating one of those, or this one, or that one, whatever. So, by the time I've thrown the outer one away, I may well have duplicated something on the other side and found another sample on the other side. So if I compute and I compress an ensemble of atoms, the atoms don't necessarily keep to their own basin or peak. They can jump. And indeed, by the time I've got to a smaller region, I'll have rather few here and here, and by the time the tide of the ocean has risen above this low peak here and submerged it, all the points have been over here. So you can't communicate, the points can move from one mode to another, even if your program can't communicate. That's what you want, of course, because if they can't communicate, you get stuck. So that's it for that. Any problems about that before I move on to Hamiltonian Monte Carlo? No? Very good. I hope. Okay, the other bit of 20th century is exploration. Oops. Hamiltonian Monte Carlo. Very impressive. Physics-based. Well, physics-inspired. And the idea here is to model exploration of a likelihood function with kinetic theory of gases. So you're thinking of a gas with molecules in it, samples, moving around in a potential field. The obvious picture is gravity. Here's the ground. Here's the atmosphere, which gets thinner as you go higher, because you need to give molecules energy to get them up there. So the density of air, the probability of finding your molecule at a particular place, is proportional to exp of minus a potential energy. The exponential form comes from physics, just believe it. And at whatever temperature the air is, let's say unit temperature, the probability of a molecule having any particular velocity is isotropic Gaussian. Okay? That's where you start with kinetic theory of gases. And it works, you get, exponential in height, which we all know, and that's it. So instead of just having a position x, our individual molecule that we're tracking has not only a position, but it's also got a velocity. It's a projectile. And the density in this joint space is density in x times density in v. They're independent things. That, again, the fact that they're disconnected is physics. But this is an exp of a potential energy plus a kinetic energy, so it's exp of an energy. So this is first-year physics. It's not difficult. If you want to find out, if you want to discover this and you haven't been exposed to it, it really isn't difficult. Now, so here we have a joint space. Physicists call it a phase space, but you don't need to worry about that, in which there is a total energy, some of which is potential energy, which is how high the molecule is, high energy. Some of it is kinetic, high kinetic, low kinetic. And the particle moves under conservation of energy until it hits something. It's a model. It works. That does what we want. The rate of change of position is the velocity, that's definition. Rate of change of velocity is mass, which we're forgetting about, it's 1, times acceleration. So d velocity per dt is grad of potential, that's force. Potential is the integral of force, so that's kind of trivial. And after some time, when the particle's got somewhere else, you arrange for it to hit something and start again, get randomized. And what we would like is to have a long mean-free path. I will temporarily go back to where we did have paths. Yeah, that's where we're going. Yeah, that's this picture of mine. Instead of the molecule bouncing around under a potential field which wanted it to end up there, let's try to make it go along in a straight line, and then we'll go further. We'll get more bang for our computing buck. Well, how do we do that? We start at x with velocity v, and we ought to follow this trajectory going around. We're trying to follow the black line because that's what the differential equations tell us to do. In fact, it would be a parabola when g is a constant. Well, we can't computationally follow infinitesimal steps because it would take infinitely long. So we have to discretize. How do we discretize? We use impulses. We say, right, we're here. Let's give it half a hit. We're here. Gravity is this much. Give it a hit. Give it a hit. Give it a hit. Halve it. The halves are there to make the trajectory reversible, which is what we want for trying to get detailed balance. Because if I started here with minus v primed, I would go bang, 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 and I'd end up here going backwards. So this sort of trapezoidal approximation is at least reversible, and the error in it, in energy, is actually quadratically small. But it's only an approximation. Because in anything other than this trivial case where grad v is a constant, if the gravitational field isn't just a constant, then those impulse forces won't properly model the integral that you would get by solving the differential equations properly. Because we'll end up at slightly the wrong place, and the errors will get worse and worse and worse, growing quadratically. So as a consequence of that, you need to accept or reject the final state, because you haven't got it right. So you've got to throw it away sometimes, and you throw it away with the usual metropolis condition. The energy you get out has to be not too much worse than the energy that went in. And that's the metropolis rule. And you can check out that with that correction, sometimes you'll accept that On this diagram, you would usually accept it, but occasionally you just have to go back again. And the statistics of that are correct by the time you iterate this over and over and over again. That's the metropolis balancing. You don't have to get the trials right, but if they go wrong, you know how to correct them and throw them away. Now, there's something I've never liked about this, and that's because actually, if I fire a projectile here, it's going to get slower as it gets to the top because it's lost energy before it picks up speed again. And if I want to end up sampling according to the atmospheric density, I would actually like to undersample here rather than oversample because the particle is going slower and slower and slower before it speeds up again. So it's actually doing things the wrong way round. Now, technically that doesn't matter because after we take a trajectory, we accept or reject, and we end up there, and the averaging in there will overwhelm whatever that bit of inefficiency was. But there is a bit of inefficiency there. It's not nice. Another reason I never liked this is connected with that, and that is that this is subrelativistic motion. I'm a physicist. I would like to see uniform sampling along here. So all I've got to do there is make sure the particle goes at the speed of light. Relativistic dynamics. Unfortunately, this is now mod V, it's a 1 norm, not a 2 norm, and the quadratic, the trapezoid things make errors which at least compensate for that, so the trick doesn't work. But still, there's an arbitrariness in this which comes from a choice of physics. Now, I'm not saying this is wrong. It isn't wrong. I'm just trying to, if you like, illustrate my thought processes and the sort of feeling that you might want to come to as students getting into any discipline. This is thinking critically. Here's what the professor tells me to do. Does it feel right? What happens if you tease it this way? Does it work according to the way you feel it should? Or is something a bit oblique somewhere? I found this to be oblique. So, this is the end of my talk, actually. There's plenty more I can say, but this is the end of my talk at the moment. And yes, Monday and today, I've gone through 3 topics. The random number generators that are built into our computer languages, they're a hobby horse of mine. This is just John Skilling being idiosyncratic and fussy, really. But I think in principle, we should be programming multiple random number explorations, engines. Because if we restrict ourselves to a single engine, there is the risk that a particular application, an unusual application, will resonate with it and it'll get the wrong answers. I just think single engine is inherently dangerous, and I go for triple redundancy. I mean, this thing, for goodness sake, it looks wonderful. The period is 2 to the 19,000. What is it, 2 to the 19,900 and something. Wonderfully large. You're never going to need anything like that. Well, exactly. You're never going to need anything like that. So it doesn't matter. probabilistic exploration, and really this amounts to quantification of anything, score functions, whatever, requires radial compression to come in from your prior region into the posterior, into what you want. And I prefer to compress directly in volume, prior mass. The alternative, simulated annealing, is L to the beta, a Laplace transform thing, which can't deal with phase changes, does give you an evidence that looks familiar, actually, to people who know statistical thermodynamics, but that's not a prerequisite for this summer school. You get that, but you don't really get the statistical variability anymore. So it's an inferior result anyway to this one, quite apart from the fact that it's restrictive. And then for the volumetric exploration we need, Galilean Monte Carlo, exploring along in straight lines until you hit a boundary and come out again. There's no rejection on that. The worst you get is a reversal. Can't go north or east or west. You have to come back south. And that's fine. But each step in it is an acceptable step. In the Hamiltonian Monte Carlo, it goes dot, 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 dot. Here, you go dot, 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 and end up there, which you either accept or you don't. These intermediate points are not assessed, so they can't go into any of your results. With Galilean Monte Carlo, you go bang, 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 bang. The worst that happens is they'll have to come back somewhere, but every step along there is another step, valid step within your box. It's correlated with the previous step, but it's still valid, so you still put it in to your averaging algorithms. So when you're looking for a property of X as you explore, here, Galileo will give you 1, 2, 3, 4, 5 points, or 4 per iterate. Hamilton will give you 1. So you get a smoother estimate for integrals, the expectations that you want. Hamiltonian Monte Carlo, this goes to presentation and psychology and so on, and the high priesthood making itself look impressive. You don't have to use Cartesian coordinates in a flat space to do dynamics. You can have particles going around in curved spaces with funny metrics. It all works perfectly well. The velocity gets generalized up to a momentum, and instead of having dx per dt and dv per dt being obvious things, they become Hamilton's equations, which look very impressive. Because for some strange reason, x gets changed to q, and you wonder why. But I can do exactly the same thing with Galileo. If you're in a funny metric space, well, you can still do geodesics and go around spheres and stuff. It's not a problem. Every step I've been through that. Trajectory explores uniformly. Galileo, this is the heart of the compression idea. It's invariant to relabeling the quality function. So if you want to change the score function, then it doesn't matter what the labels are as long as the shapes, the contours are the same, which the other isn't. I don't care about differentiability, I don't care about step functions, it doesn't have to be smooth, and I only need 2 vectors rather than 3 to run the algorithm. Not that that matters, but hell, simplicity. Okay, well, that's it for this topic. And although I did think I might talk about clusters and stuff, I'm not going to now, because I'd rather get across some simple ideas. The European flag there is because I'm a European and feeling rather happy at what happened last night in England. Anyway, that's it for now, and I'm open for questions. Thank you.